Good morning to everyone. Thank you very much for attending the lecture this morning. I'd also like to thank very much the organizers of the conference, Professors Pedro Moreira and Luis Reis, for inviting me to be here. I think everybody will agree that has been a fantastic conference in a wonderful Portuguese island. Thank you very much for this. I think this is so back to business. This is the outline of my presentation. I'll just say a few words about the Griffith theory. Then I will jump to the show you some cases about the importance of the cleavage fracture. From then, I will talk a little bit, an overview of especially the current understanding of the mechanism of cleavage fracture. And then this will allow to introduce a very simple continual approach to fracture. And then we will jump to the, let's say, to the main core of the presentation. It's the statistical models, probabilistic models, the Beremin approach, and then some recent progress and challenge in the within the fracture mechanics field. Okay, so I want to say a few words about the Griffith theory. Okay, I don't mean to be repetitive because everybody, I think, in this room knows about this. But last year, 2021, was the centennial anniversary of the seminal publication in 1921 of the seminal work of Alan Griffith. Okay. And the importance of Griffith's work, it's not only related to the first time there is let's say a formal framework for addressing cracks in materials in bodies, but I think was the first time there is a connection between the fracture strength and the crack size. This was before, of course, especially after the Industrial Revolution with the introduction of steel and other materials. Most of the work was kind of semi-empirical. And that was the first time that we have this connection between fracture stress and microcrack size, which you can even interpret as the first time that we saw a kind of length scale in the framework of fracture mechanics. And then later in 1949, Orovan, is also very famous work here, addressed the question of some limitations of the Griffith theory, introduced the plastic term here to account for plastic dissipation. But it's interesting to know that actually Orovan did not make any, did not address these limitations or the Griffith theory within the main body of his work. Actually, this appears in a footnote, very small footnote here, when he mentions something about the limitations, the difference between the predictions and the actual fracture strength, and then he suggests that that something must be affecting, which should be the plastic term in terms of the plastic dissipation due to plastic work. And so despite the limitations, we all agree here that Griffith's contribution is unquestionably the forerunner of all theories based on the presence of loss to account for the loss of strength. And then a long time passed, but this was let's say the concept that actually provided the impetus to develop what we know now by linear elastic fracture mechanics. That was previous work by George Irving, which, by the way, had the honor to meet just a little bit before he passed away. That was in the US in 1957. And it's interesting to know that even George Irving recognized these as, and I quote, according to his own words, the modified Griffith theory to somewhat brittle materials. That was kind of interesting. So that's why it's just to, as I said, just to pay a small tribute to Griffith's work because of the centennial work, okay? So let me show you then a little case about cleavage fracture. And why it's still a very important failure mode, even though it's one of the most fundamental failure modes, probably is one of the most understood failure modes, okay? But I want to show you some cases. So cleavage fracture is perhaps the most dangerous and in some cases, spectacular form of material failure. And one of the key issues here is that the cleavage fracture often occurs due to small, but very often neglected cracks or defects, such as microcracks, inclusions, weld flaws, a highly stressed region. So most of the time it will show up during the in-service operation of the structure. That's very worried. It's a matter of strong concern. So despite all these advances, novel materials, new materials, high-strength steels, high-strength alloys, cleavage fracture will continue to plague the engineering field, unfortunately. Is something that we very often cannot avoid. We can mitigate it, but not avoid in many cases. So a few cases here. This is a pressure vessel, very common in the petrochemical industry. So this is a brand new, it's a fabricated pressure vessel. So before any pressure vessel can be put in service, it has to be hydro-tested. So this was the failure. You can see here very brittle characters of brittle failure, no plastic deformation at all, just because of the hydro test. And as you may know, the hydro test is under the yield stress. So it's actually it's in a pressure which is a little bit above the let's say the operational pressure, but it's not that high that will burst the vessel. Okay. The other case that I want to show that it was a very nasty accident. At that time was one of the largest accidents in the steel industry in the world. It was in 2002. This is a high furnace. I'm not going into detail how steel is produced. I think everybody knows more or less how this is produced. So this is the furnace. This is the transportation belt. And those three vessels here are the hot blast stove. So for the process to operate continuously, they have to, let's say, blow hot air every 8 hours. So one is blowing, the other is filling up. And this is the dome of one of these. That was number one, actually. It's number one, number two, and number three. This is the dome of number one. You can see here the size of the engineers at the field. To see the size of this piece is about 150 tons. So it's exploded, traveled over the transportation belt, and landed about 250 meters from the site here. And then you can see here the damage in this is the circumferential girth weld of the vessel. I'm not sure you can see very well here, but this is what the fracture started. It started by a stress corrosion mechanism here. It evolved very slowly over time, and then finally, actually was March 22, just exploded by cleavage fracture, by brittle fracture here at the thickness. And the third case that I want to show is the Hanshin earthquake that occurred on January 17, 1995 at approximately 5:40 in the morning. Huge losses, in huge structural losses, okay? And one of the aspects of this earthquake was a large ground motion. So the large ground motion will imply large plastic deformation, which will activate the small defects that were present in the welded joints. So most of those structural losses were caused by mainly the connection between the column and the beam at the welded joint here. So you will see, I just picked a little cases here. So you'll see a lot of fracture, brittle fracture arising from the welded joint and just propagated through the whole section of the column or the beam. Okay, so because of the importance of cleavage fracture along all these years, so since the I'd say early 60s, there is a great deal of work on identifying the micromechanism of cleavage fracture. So, and that's because understanding the microcrack nucleation propagation is key to bridge the gap between global behavior and fracture at the micro level. So any decent model would have to look at the connection between the global behavior and the micro behavior. And that's because we need a proper description of the critical event which is controlling the local failure. And here we are focusing the attention on micromechanisms which are operating on the scales of 1 to 100 micrometers. Usually it's the size of a few grains in the steel, especially in the ferritic steel. Here, okay? We know now from these early works in the 60s that the unit plasticity, even though the material is globally brittle or elastic, you need local plasticity to activate this slip-induced dislocations, so they will propagate, and usually they will pile up at the grain boundary. And thereby, because of the pile-up of these tensile stresses, they will nucleate a microcrack. So that's how it works. So we have many carbides here, you can see here in the grain boundary, and those carbides, especially, so the grain boundaries will serve as very strong barriers, obstacles, okay? And that was the Griffith notion of microcrack propagation comes into play. So to block the motion of slip, so they will produce the tensile stresses which are required for microcrack nucleation. So we can see that especially for not so very tough materials where probably ductile failure prevails, we're going to see a lot of grit of the Griffith concept playing a role there. And here is the formation of a Griffith-like, what we call, and I'll refer to this very often during the presentation, the Griffith-like microcracks. So you can see here the grain boundary, okay? By the way, the focus is on steels, okay? So we're talking about essentially a ferritic matrix. And that's because, although it doesn't appear so, but it still remains as the backbone of engineering structures. Even though we are developing new alloys, high strength non-alloys, etc., but still the backbone of the ships, offshore structures, pipelines, pressure vessels, etc. Okay. Then you can see here the boundary. You see here the crack propagating through the boundary. Okay. And that's what we would normally call the Griffith-like microcracks. I'll get back to this later. Okay. So this is how then it works. We can just capture the main controlling mechanisms and interpret cleavage fracture as a three-step process. So is slip-induced cracking, usually brittle particles, and for most of the, let's say, structural steels, low-carbon steels, usually it's a carbide. Usually it's a carbide which is sitting at the grain boundary. The propagation of the microcrack along the particle matrix interface and then across the grain boundary when the process is, let's say, complete, and the propagation along neighboring grains. So just to give you an idea of how the boundary is a strong obstacle. It can be interpreted in terms of the, let's say, the fracture energy for crack propagation in terms of the Griffith theory. You can see here the single crystal for iron. It's about 2 joules per meter to the square. The grain boundary between ferrite and ferrite is 56. And what is probably is of interest in our work is the carbide ferrite boundary. It's 14, so much less or much smaller than the ferrite. Okay, and also we have to consider, which is one of the main focus of our work, is the effects of plastic strain. Okay, then we can see here, for example, the work of Lindley in 1970, where he shows the number of microcracks that nucleate from broken carbides with strain and with temperature. And you can see here a very significant increase in the number of microcracks, the broken carbides, as you increase the strain. And the same here in a more recent, not so recent, but anyway, of Gerland. You can see here also the strong increase in broken particles with the increase in strain. Okay, So the thing is, how do we incorporate all these key controlling effects into an engineering level approach? Okay, it has to be relatively simple. It has to be effective and robust. Doesn't depend too much on model details, parameter calibration, etc. It should require modest effort, experimental data to obtain experimental data, analytical efforts, computational efforts, and in my opinion, most important, it has to be a good predictive capability. In other words, what we measure, what we develop at the laboratory, in our computer, has to be transferred in a very robust way to the real world, to the real structure. Okay. And there have been some proposals. Of course, it's much more than what I'm going to show, but I'm going to show you, let's say, some key deterministic models. Okay. I need to keep track of the. Just a second. Okay, so I'll talk about some continuum models, which are really where is the? Oh, yeah. Which are really deterministic models. Okay. First is the critical fracture stress. Probably everybody who is dealing with cleavage fracture once in their lives have used the critical fracture stress. It's very simple. Okay. And probably one of the most widely adopted, widely known critical fracture stress model is the RKR. It's the Robert Ritchie, John Knott, and James Rice model, where they say that you have to build enough crack tip stresses. You have to build enough stresses, and usually this buildup should cover at least 2 grains. Okay, so actually the breaking of a carbide here, it's a very schematic illustration. The breaking of a carbide here is a necessary condition, but not sufficient. So for cleavage to occur, so the Griffith microcrack, for the broken carbide needs to spread through at least 2 grains. Okay, so it's a good model. Does not allow us to do much prediction, but generally explains the so-called constraint effects on fracture toughness. That's why shallow crack specimens will have or will display larger toughness, because you have to load your specimen with more J to build the stresses up to a point where you reach your fracture stress. The other, let's say, continuum approach, and it's a very popular approach, is a multiparameter description. Okay, basically we have the JT approach, which is based on the T stress, the elastic T stress. We have the JA2 approach, which also is a multiparameter description, and probably the most popular is the JQ theory, which was proposed by O'Dowd and Shi, Noah O'Dowd and Feng Shi in 1992. So usually it's based on a 2 parameter. So this comes from self-similar boundary layer fields, etc. So J sets the amplitude of the crack tip stresses, and the second parameter, the Q parameter, sets the difference field. So actually it's an approximate description of the effects of constraint. Okay, because in this approximate description, the Q parameter is actually a hydrostatic stress, which is measuring the difference fields between a high constraint crack tip field, usually AGR field or boundary layer, if you use a finite element analysis, and so. And these are the JQ trajectories here. A CT specimen, okay, we are plotting minus Q because Q is negative. So this is just to give a more, let's say, nice picture of the diagram. So the CT is high constraint specimen. So actually the CT specimen within the standard specimens, ASTM, British Standard, ISO, the CT is by far the highest constraint specimen. Then comes the SCB with different crack size, the SCT, which is becoming very popular, especially in the oil and gas industry, and then we have our structure here. So that's the meaning here. Okay? So as you lose constraint, your Q becomes more negative. And one thing that we can do with the JQ parameter or theory is to build JQ toughness locking. Okay? Basically, you have several JQ trajectories for several specimens, several configurations. You can think of these as your structural component, can be even under biaxial loading, doesn't matter. And then you do a lot of experiments, and then you build this, this gray area here, which is probably the upper bound, the lower bound. What for your material, all the data would fall into this gray area. Okay, it should work. The problem is that, or the limitation is that, this will require many experimental data. The Q parameter is actually a 2D parameter, so actually it's not 3D, it's a plane strain 2D parameter. But perhaps most importantly, it doesn't capture the what we call size effects. Okay, that's what I'm talking about. There is strong effect of specimen geometry, specimen size on toughness. Here you can see here a 1T specimen, okay, standard SCB bench specimen, 3-point bench specimen. And this is the pre-cracked Sharpie specimen. And you can see clearly the effect of the specimen geometry. For example, on the master curve reference temperature here, okay? This is for an irradiate high-strength steel from Oak Ridge. You can see here that you go from the 1T to the pre-cracked Sharpie, huge difference, or potentially huge differences in your T0 evaluation. Okay, and this is the picture here. This is you can see here what's happening here. This is the 1T 1 inch, okay, 25 millimeter SCB, and this is the scale of your principal stress contours. Okay, which you can think of this as your fracture process zone. You can see here a very huge process zone for the SCB specimen, high constraint, and the same out of plane constraint. This is for a deformation limit of 60, which is well inside the small scale yielding conditions. Remember that the master curve specifies deformation limit of 30. And this is the pre-cracked Sharpie. You can see here the principal stresses. The fracture process is much smaller, okay? Which will obviously explain the difference in toughness ratio. Okay, so because of this, okay, there is a trend to go towards probabilistic models. Then we have to consider some statistical aspects of fracture. So implied in the Griffith theory, so again, our Griffith concept here is the presence of very small cracks as the precursor of fracture, okay? And an important aspect raised by the Griffith theory is that the number of the most effective cracks in the specimen is actually relatively small, okay? So not all microcracks will trigger cleavage. That's a very important concept that's somehow implied in Griffith's theory. And then you can see here the distribution of carbides. That's very important because fracture is random. The carbides, which may eventually become a microcrack, they are randomly oriented, and they are random in location, so they can also be oriented in space. This, of course, is a 2D image, okay? And the actual picture is like this. I'll go back to this later, but this is the carbide distribution from the Euro material that was made in 2005, and you can see here the distribution of a microcrack size. Okay. Oops. Okay. That's the picture then at the crack tip. Okay. You consider a random orientation or a random distribution of broken carbides inside the process zone. So usually we consider the process zone as 5 to 10 times the CTLD. So I would say that 5 times a better number, okay? Where fracture is controlled by the unstable propagation of a broken carbide, which is randomly located and possibly oriented in the space, okay? And that's the fundamental probabilistic model here, okay? You see here the I'm not going much into detail of this, but you can use some probabilistic theorems, assumptions, and you come up with the elemental failure probability for your elemental volume. Or you can see here the volume, the volume of the element, and this is very important. This is the PDF, the probability density function for the microcrack. So in this approach, defining the PDF for the microcrack is key in the approach. And it is very interesting because you don't see this written in many papers around there. The choice of the microcrack distribution is actually not arbitrary, okay? Because we are dealing actually with the statistical theory of extreme values that was, let's say, formally introduced by Gumbel in 1958. And this is connected to the distribution of smallest values. Okay, that's the reason why we end up in the with that particular distribution within the Beremin model. But however, many years ago, it appears that was Pierce, 1926, that was the first one to introduce the concept of weak link. He was working for the British cotton industry. So he used actually a normal distribution, a Gaussian distribution, to describe the breaking strength of cotton yarns. Later, much later, Weibull, that everybody also must have heard of his work, he applied the same weak concept but he used a different probability distribution which helped explain the so-called size effects, okay? And then from this comes the Beremin model. Okay? The Beremin model actually builds upon those probability concepts. You arrive at a failure or probability of failure probability distribution for the principal stresses inside the process zone. And it is very, very important, as I told you. It's not arbitrary, it's not by chance that in the Beremin model, this asymptotic distribution was employed. Okay, because this is connected to the statistics of extreme values. Okay, then by using a simple Griffith criterion for the unstable propagation, and also remembering or noting that the Weibull modulus, this parameter here, is actually connected to the Microcrack distribution. Okay, then the Beremin model coined the term Weibull stress. Okay. So this was introduced by the French Beremin group, was Professor Pinot, so unfortunately he's not here, Francois Mudry, and others in 1983, okay? Actually, this is a closed form, that's very nice. It's a closed form which derives directly from the assumption of a Cauchy type asymptotic distribution for the microcrack size. And one of the nice thing about the Beremin model, which, by the way, the Beremin model is, it probably is a French national pride by now, because most papers by our French colleagues somehow will refer to the Beremin model, which is a very nice thing. And that's because it's relatively simple and yet highly effective, especially because it relies on nonlinear finite element analysis. So you can literally include many effects in your analysis, okay? Such as strain hardening, load rate effects, thermal loading, if you want, okay? And that's usually the kind of predictions that we get. This is the Weibull distribution for a pressure vessel steel, deep crack SCB, and this is the pre-crack Sharpie. And this is usually the prediction that we get from the Beremin model, okay, from the Weibull stress, from, for example, the pre-crack Sharpie. Now you can see here that although it's a little conservative, okay, it still does a very good job, in my opinion, because remember that you were going from, let's say, 50 kilojoules per square meter to essentially 300 kilojoules per, so it's a 6-time difference, okay? So the Beremin has proven effective in several fractal problems. It uses, or you end up, if you follow the procedure, two-parameter Weibull distribution. And there are some critics, among them Teddy Anderson. Teddy Anderson is a big critic of the two-parameter Weibull distribution. And the reason is because the two-parameter does not consider a threshold value for the fracture stress. In other words, you have a finite probability very close to zero load. That's the meaning, okay? The parameter calibration, particularly the Weibull models, may be tricky. That's one of the drawbacks, and often cumbersome. So it's not easy to get the right parameters. But most important, the Beremin model assumes that all microcracks in the fracture process zone will nucleate immediately upon yielding. So once you get the yielding, all the broken carbides are there. Okay? So because of this limitation, we proposed a modified Weibull, modified Beremin model, which has essentially the same form, but then we look at the distribution and say, okay, let's assume that only a fraction of those microcracks are eligible to nucleate or to trigger cleavage fracture, okay? And that's what we did. We incorporated the fraction here, which is a function of the plastic strain, which effectively drive the cleavage fracture process. It preserves the closed form for the Weibull stress, which is very nice because you can use the same framework, and it's highly effective in incorporating the potential effects of plastic strain and constraint loss, as I will show you here. This is the predictions for a 515. This is a standard pressure vessel steel. Okay, this is again the 3-point bend specimen here. This is the predicted distribution using the modified Weibull stress with a particle distribution model, which describes the effect of plastic strain. I'm not going into detail this because of time. And this is the same prediction using the Beremin model. Okay, you see here that Bob Dodds used to refer to these as the overshooting. I don't know what he means by overshooting, but he calls this overshooting when the prediction is too conservative. Okay, and that's because of the effects of plastic strain associated with constraint loss. Another possibility is to, and that's a more refined approach, is to actually include the microcrack, the measured distribution of microcracks, okay? So again, we are building upon the elemental failure probability, but instead of using a fixed assumption or an assumption for the microcrack distribution, we are describing or measuring the microcrack. And then we just end up with this kind of distribution, which is based on the explicit evaluation of the microcrack distribution like this, okay? Where this n sub c is the number of microcracks which become Griffith-like, the number of carbides which become Griffith-like microcracks. Okay, almost done. So that's just show an application. This is the Euro material again. The 1T CT, the half CT, 1T CT at different temperatures. So our goal here is to predict the effect of temperature on toughness, not constraint loss, okay? Again, this is the measured microcrack distribution here, okay? Again, from the investigation that was done on the Euro material in more than 10 years ago. We assumed a Weibull distribution to describe. That was a fitting, okay? That was fitting of the previous, fitting of this previous distribution. Weibull distribution with two parameters, alpha sub c and beta sub c. And we employed the Pareto distribution. By the way, it's a very flexible distribution, the Pareto distribution, to describe the effects on the effects of plastic strain. That will give you the number of eligible microcracks. And that's the prediction that we have here for the minus 110 and minus 90. Okay? So, of course, there is a lot of scatter, but you can see here that the average, the predicted distribution is actually quite good in this case. Okay, so what are the challenges for engineering applications? We need a simple and yet effective parameter calibration. We need to get rid of the mesh dependence. This is a problem because remember, you are raising the principal stresses to a very large power. So small the small difference in your mesh may, not always, but may cause some problems in your finite element analysis. We also need to extend this procedure for defect assessment. For example, incorporate these in Bridge Standard 7910, API 579, and other procedures, FitNet here in Europe. Address materials with macroscopic heterogeneity, for example, weldments. The heat effect zone, which is a particular region of concern, and the extension to other brittle fractures. So regarding this, one potential candidate is hydrogen embedded in the pipeline and pressure vessel infrastructure. You know, we have many papers and many sessions on this conference about hydrogen embeddment. Okay, so everybody by now is very familiar with the material degradation caused by hydrogen. Okay, and one of the main concerns is that this degraded material fails very early and possibly catastrophically, okay? And so, this is some case here, okay? This is X100 pipeline steel. By the way, it's a very good material. This generation of X100 pipeline steel, they very high strength and very high toughness. And that's what happens here. This is the K1C, okay? This was measured by Brian Summerday at Sandia National Lab in the US. You can see here no hydrogen, and you see here the effect of the gas pressure. It's very interesting because even small amounts of hydrogen will just drop your fracture toughness, and you can see here the difference in the microstructure. It's a dimple, okay, so it's almost ductile, and here you can see signs of intergranular fracture. And that's what may cause, for example, in the offshore industry. This is a flexible pipe, okay? I'm not going to detail this, but this is not rigid, it's a flexible pipe, and the inside is a polymer, and the outside is the tensile armor, which is made of ultra-high strength steel, okay? And they are very susceptible to hydrogen embrittlement, and that's something that can happen when the nasty elements, they permeate through the polymer and will reach the armor, okay? So hydrogen embrittlement, as again, all we see in these many sessions and panels here, there are a number of mechanisms, no consensus yet. Nobody. Okay, I'm done. So it appears that we are converging to these two key driving mechanisms: the help, localized plasticity, and the induced decohesion. Okay, and I think that many will agree that material degradation will actually occur by the synergistic effects. So I think that's one area that the local approach will perhaps be well suited to address this kind of problem. Okay, and some closing remarks. Okay, that I will just skip this because the chair is pressing me to finish the presentation. But the message here is that there are still some room for advancement in the methodology, because we need to understand better the fundamental concepts, and I think that's probably one of the messages of my talk. Okay, anything that you do in your model should be tempered by the need to develop a simpler and highly effective engineering model. Okay? I'd like to finish by acknowledging the Professor Bob Dodds. He who have been working. It's a very long time collaboration, local approach model, computational fractional mechanics. He's now retired and living in his very nice home in Colorado, going fishing almost every weekend. To the many colleagues and students, some of them are here, Professor Jipkov and others who also have worked with me in many ways, and also these Brazilian supporting agencies. And just to remind you that next year we are having the International Conference on Fracture in Atlanta. It's organized by Professor Robert McMicken, University of California, Santa Barbara, Professor Saxena from Georgia Tech. And we are organizing very nice symposiums about all problems in fracture. So please be sure to participate in this conference. Okay, thank you very much for your attention.